Okay, let's see. Okay. We are going to work on basically Lewis structures the entire time. Now, your last hour assignment on Lewis structures, it's a beast. So by a beast, it's a little bit of a pain figuring out how it wants it. That's going to delay some time. I think the average time on that is 3 hours and 20 minutes. The other issue is this. The lab next week is a beast. It's like 13 pages. In order so you can proficiently do the lab, we are going to work on Lewis structures, which is the lab. So by the time we get done today, I'm going to have pretty good confidence. I'm hoping that you can nail that lab. Because that's what I'm concerned about. And you can work some of that lab ahead of time. So today we're going to work on Lewis structures, which again, pretty much is the entire lab next week. So I want to get you to that point where you're going to, I don't want you to walk into the lab and say, oh, what's going on? So my goal today is basically do Lewis structures, and then we're going to talk about polarity and bonding and all kinds of things that go with that. So that is my goal today. I looked at the lab before class, so I want to show you a video, but that's what we're going to try to accomplish today. Hopefully everybody has a blue sheet. The blue sheet is the key to everything. So if you don't have a blue sheet, come down and get a blue sheet. So, we left off, we just started doing fluid structures a little bit. And we did CH4. So CH4 on a piece of paper, this CH4, if I draw this out, you'll see it drawn like this, where it looks like your bond angles here are 90 degrees. But you're looking at this rendition on two-dimensional paper. CH4 is really this. This is a completely symmetrical molecule. Whichever way I flip this, it looks exactly the same. So if I turn it sideways, this angle right here would be about 90, right? So we're looking at a bond angle here. This is 4 bonding domains, 0 non-bonding domains. We're looking at an angle of 109.5. Again, this is in 3-dimensional space. Your paper is 2-dimensional space. No matter which way I flip it, this is a completely symmetrical molecule. So this is CH4. So the best thing we can do is just continue where we're at and just work on these so you get a handle on these. Let's do the next one here. We have C, and we can write it right here for our skeletal structure, which is the first thing to do. So you've got C, and you've got Cl, and now you might see this and say, well, do I put the Cls across from each other and the Fs across from each other? And the answer to that, it doesn't matter. Again, when you see this in 3D, if I put 2 different ones on here, there's no way they're going to be truly 180 across from each other. This is the same, the arrangement of the atoms around the central atoms will be exactly the same. Two of those are going to be chlorines and 2 of them are chlorines. So if you draw this dash, what does each dash represent? When you connect them, there is a pair of electrons for each dash, if you draw it that way. So that's what we'll do. The central atom here in the middle is going to be the lone atom 9 times out of 10. So we can do Cl like this. We can do F and we can do F. That is step 1. Step 2 is to count your total valence electrons. So carbon has, we've got 1 carbon atom, and perhaps I should do it this way. It is in group 14. So if it's in group 14, how many valence electrons? 4, right? Chlorine is 2 atoms of chlorine in group 17. So how many valence electrons? 7. Fluorine is 2 fluorines in group 17 as well. And I'm not going to do this again, but realize we're doing the ones place, right? We're doing the ones place matches the valence electrons. So I've got 14 and 4, 18 valence electrons. That is step number 2. So I'm going to go to my sheet to make sure I'm following this. So I'm going to grab another one here. All right. So we did a skeletal structure with dashes. And we put carbon as the central atom. Got our total valence electrons. Step 3, draw a bond between the central atom and each surrounding atom. A single bond is a pair of electrons. So that's what we're going to do here. We're going to put carbon in the middle, and we're going to do a pair of electrons here, and we're going to put the Cl. We're going to put a pair of electrons here and put a Cl. Pair of electrons here and put a Cl. Oh, no, one of these. I got to go F, and I got to go F. Sorry. I made it look a little ugly. We got 2 Cls and 2 Fs. Now, next step. So far, I have 8 electrons, right? I've got 80 electrons total out of 18. No, 14, 28. I got 32 there. Oh, man. This is 32, right? When somebody throw a pen at me. This is 32. I just added, I didn't take into account the 2. 32 valence electrons. 32. Hopefully somebody needs to stick in their head before me. Okay. We've accounted for 8 out of 32. Step 4. Place lone pairs of electrons about each terminal atom to complete their octets. An octet is 4 electron pairs or 8 electrons. Hydrogen can only have 2 electrons. Okay, so here we go. I'm going to add 6 more around this chlorine. Because now, that would make it 8, right? 8 electrons. This completes their octet. What's an octet? 8. So I'm working on the terminal atoms on the outside. I'm completing their octet. There's 2 in this bond. They need 6 more total. Same way over here. This chlorine needs 6 more total. Chlorine needs 6 more total. And this chlorine needs 6 more total. If at this point, how many total electrons do I have? 32. Everybody's happy as sugar pie because in the carbon has a total of how many electrons? Carbon has 8 in the middle, correct? My terminal atoms. And we've got 8 there, correct? We've got 8 here. We've got 8 here. We've got 8. Everybody has 8. That's the best party we can have. Everybody's happy. Everybody is happy as they can be. It's useful. Everybody has 8. How many? So now we go to this. How many bonding domains and non-bonding domains do we have? And all we care about is the central atom. How many bonds does the central atom? How many bonding domains for the central atom? 4, right? Domains. It's got 4 bonds. Every pair of electrons is bonded. This is 4, 0 again. So for a 4, 0, you're going to check your blue sheet. And a 4, 0, the shape is going to be tetrahedral. The bond angle is going to be 109.5. Hybridization we're going to talk about is sp3. Now, let's talk about this. Electron pair geometry and molecular geometry and angles. The electron pair geometry is, I'm going to start separating this. This is a 4, 0. There is, if you just look at the electron pairs in the middle, how many electron pairs do you have? 4. So this is tetrahedral. Molecular geometry is 4, 0. That is tetrahedral. 9.5. We'll talk about this last column here coming up. Okay. Well, let's do the next one. And here is my note on electron pair geometry as well. The electron pair geometry is the geometry assumed by all the valence pairs around the central atom. Around the central atom. Now, let's do this example. We have NF3. When you draw this out, it's nice to try to keep everything as far apart as possible. And if you do this as far apart as possible, you're going to put these at 120 degrees. If you only have a central atom with 3 around it, you should try to space them out as best you can. Now, I'm not saying that is 120. We'll write it out and then we'll find out. Remember, always remember, you're looking at a 2-dimensional sheet of paper to represent a 3-dimensional molecule. All right, total valence electrons. I'm not going to write those 14s anymore. That's the first time I've ever did it, and I screwed up here. So nitrogen is in what group? Nitrogen is in what group? 15. So that's 5 valence electrons. Fluorine is in group 17, correct? We've got 3 fluorines. It's in group 17. How many total valence electrons do I have? 26, yes? 26, all right. I did not send that little sheet around. December 1st today. I'm just going to add that. Well, I'll just do it. I'll send it around here and just lay down. 26. All righty. Step 3 right here. Let's bond these pigs, huh? We've got a nitrogen. We're going to put a pair of electrons. Now, watch how I do this. I'm not going to put them 120 now. We're going to put a fluorine there. We're going to put a fluorine here. We're going to put a fluorine here. That's step 3. Go to my sheet again, because I want to make sure you can follow this sheet. So 3, draw a bond between the central atom and each surrounding atom, single bond, that's what we just did. Place number 4, place lone pairs of electrons about each terminal atom to complete their octets of 8. So let's do that. I haven't a good party yet. Fluorine is happy. All the fluorines are happy. Why are all fluorines happy? Every fluorine has how many electrons around it? 8. What about nitrogen? Not good. 6, right? We got an issue. Let's see what we got here, though. How many total valence electrons do I have down so far? 8 times 3, 24. Yes? How many more do I got to go? Because I need 26. 2 more. Let's look at what we need to do next then. Here's the directions. Number 5. If there are more electrons left, place them as lone pairs on the central atom. This will sometimes lead to an expanded octet. Now, what is an expanded octet? Greater than 8 electrons around that central atom. And it actually says this here, an expanded octet, 5 or 6 electron pairs. So that's 10, 12, 14 electrons around the central atom. Only the central atom from the 3rd period and above have expanded octet. So let's go back here. We have 2 more electrons. What are we going to do? We're going to plot those babies right there. Now I have 26 electrons, right? 26. Everybody's a winner. Everybody's happy. Now, how many bonding domains on the central atom? 1, 2, 3, right? 3. How many non-bonding domains or non-bonding pairs? 1. This is a 3-1. Look at your blue sheet for a 3-1. What's the shape? Trigonal pyramidal. Angle now is 107.5, hybridization sp3. Okay, so my hybridization is sp3. Now, what is my electron pair geometry? How many possible bonds can the central atom have? 4, right? Got 4 bonds on the central atom. So the electron pair geometry, you treat it as a 4-0. So my electron pair geometry is tetrahedral. But my true molecular geometry is a 3-1, and that 3-1 is see this pronounced both ways, trigonal or trigonal and pyramidal. Modify this now. All 7.5. So what happens is this. This should make perfect sense. If we have 4 bonds, if it's a 4-0, what is my bond angles all? 109.5. Agreed? 109.5. If I take one of these off, I take one of these off, and I've got this pair of electrons that's not streamlined because it's not bonded to anything. Now think about this. You have 2 bonding electrons here, correct? They are attracted to the positive nucleus here. They're attracted to the positive nucleus here. They're somewhat, I would call them, streamlined. They're not taking up a huge amount of space. When you have a non-bonded pair, it's huge up here. It's taking up a lot of space. And what that does is all this big negative cloud that's unbonded will repel these 3, and it'll change the angle just a little bit, not a lot, right? So if you kind of repel these all together, I go from 109.5 to 107.5. Right? And again, this is in 3-dimensional space. This is not 120 degrees away from each other, right? 3-dimensional space. Let's do the next one. Next one is a little bit different, but this is the first time we have an ion. So recognize that we have this charge right here. So to do this, valence electrons. Nitrogens are group 15. Hydrogens, 4 times 1. Yes. Now, let's go up to the top. Add. If you have a negative ion, you add. You have a negative charge. If you have a cation, which is a positive ion, we need to subtract. So for total valence electrons, if you have a negative ion, you got to add. If you have a positive ion, we're going to subtract. We have a positive ion right here. So we need to subtract 1 electron. If we subtract 1 electron, our total valence electrons is 8, right? 8. All right, so let's do our next step. We're going to put a bond. What happens? How many electrons do I have total so far? 8. How many am I allowed? 8. Is everybody happy? Everybody is happy because realize hydrogen only wants 2 electrons, not 8. What's the closest known gas to hydrogen? Helium, right? Helium has 2 electrons. Hydrogen's happy here with 2. This hydrogen happy here with 2. 2, 2. Everybody is absolutely happy. Now, since this is an ion, you will see something like this. You will see a bracket around this. Outside the bracket. This is what you see if you Google Lewis structure. This is ammonium ion. So there are no multiple bonds. There is no resonance structure 1, resonance structure 2. We'll get to all that. My bonding domains is 0, yes. My hybridization for a 4-0 is sp3. We'll talk about that. What is my electron pair geometry? In my electron pair geometry, by the way, it's always going to be a 0 down here. That's just the way. It's always going to be one of these 2, 0, 3, 0, 4, 0, 5. All you're doing is looking at how many pairs are around the central atom. In geometry, you're only looking at how many pairs are around the central atom. That gives you the possible bonds. So, my electron pair geometry is a 4-0. And what is my true molecular geometry? 4-0, correct? They're both 4-0. So 4-0, 4-0. Both of these are tetrahedral. And what is my bond angle? So hopefully nothing overpowering yet, right? Nothing overpowering. CO2. Put carbon in the central atom. CO2. We've connected it. Total valence electrons. As oxygen has 2 times what? 6. It's in group 16. So hopefully I do the math correctly and I get a total of valence electrons. Whatever that works for. Yes. 16 valence electrons. All right. Let me put my steps in again. I did my valence electrons. Step 3, draw a bond between the central atom and each terminal atom, surrounding atom. I'm going to come over here and I'm going to go like this. I'm making it sideways. There's a little bit more room. What's step 4? It's step 4. Yes, step 4. Place lone pairs of electrons about each terminal atom to complete their octets. Sound good? So I'm going to come out here and like that, right? Just put 8 around the outside atoms, the terminal atoms. Who's happy and who's not so far? Oxygen's happy as heck, right? Oxygens are partying up a storm. Carbon doesn't look good. This carbon only has 4. How many does carbon have to have? 8, right? Carbon has to have 8. How many more electrons are we allowed? How many electrons do we have so far? 16. Are we allowed any more electrons? No. So you can't just add electrons to the central atom. You cannot just crank electrons in at that central atom. Let's see what we're going to do. We're in kind of a pickle here, huh? If there are more, so we just did number 4, right? We placed lone pairs, the electrons around each terminal atom. We did that. Number 5, if there are more electrons left, there are not more electrons left. We go to step 6. If the central atom has an incomplete octet, it does because carbon only has 4 electrons, right? Well, number 6, if the central atom has an incomplete octet, use the electrons from surrounding atoms to make double or triple bonds. Do not add any electrons. Borrow them from other atoms to make multiple bonds. Only carbon, nitrogen, oxygen, phosphorus, and sulfur have multiple bonds. Okay, so here's what we're going to do. We're going to form multiple bonds. And do that. Borrow 2 of these right here, and I'm going to put them in there. And it doesn't matter which way you do this. I'm going to put those 2 in there. So when I do that, now let me draw this first one out. When you do this oxygen right here, if you put them as far apart as possible, these pairs, you kind of put them at the corners like this. That's kind of okay. And I got to do the same thing for my other oxygen. I've got to put 4 in here. Here's my carbon dioxide molecule. Now, how many bonding domains? How many bonding domains? How many non-bonding domains? Now remember, it doesn't matter if it's a single, double, or triple bond. That is 1 bonding domain. So this molecule has 1 bonding domain here on the right, 1 bonding domain on the left. That's 2 bonding domains. How many pairs are not bonded? 0. This is a 2, 0. Are we good with that? 2, 0. Doesn't matter. Single, double, or triple is 1 bonding domain. What is the hybridization for a 2, 0? SP, yes? What is my electron pair geometry? How many possible bonds as drawn can you do? Just 2, right? This is a 2, 0. What is my true molecular geometry? 2, 0. Those are linear, 180 degrees. Let's go down to VR. Well, we'll try VRF3. Actually, let's go down to VRF1. Let's do this one. So you've got a VR here. 5 bonds around it. Total valence electrons here is 7 for the bromine. Chlorine is 5 times 7. 42, huh? 2. Right? Let's put our BR in the middle. Let's space out our F, 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 F. I've got 5. So I kind of space those out. We're going to put a pair of electrons in here. All right, let's complete our octet on the outside, right? So you're going to put 6 around each fluorine yet? We're going to put 6 around each fluorine. What's my total electrons I have so far? We got 42, right? 40 out of 42, yes? We're allowed 2 more. Where are we going to put them? I'm just going to put them in here around the central atom somewhere. I'm just going to stick them right here in another color so they show up. I do multiple bonds with group 17 elements anyway. We know we're not going to have any multiple bonds. We do not have resonance structures. We're going to get to that coming up. How many bonding domains do I have? I've got bonding domains and non-bonding domains. I've got what? 5, 1, don't I? I've got to put these columns together. I'm trying to get all this to print out as one unit, but I've got to combine something. If I have a 5, 1, what is my hybridization? P3D2. I'm going to explain that coming up. What is my electron pair geometry? Possible bonds could I do? I have 5, but I got another pair of non-bonded, right? So this is a 6. I could have 6 for my electron pair geometry. So for my electron pair geometry, think of it as a 6, 0. For electron pair geometry, you're just looking at how many pairs, and to get the exact arrangement on your blue sheet, you just slam a 0 in every time. Electron pair geometry is going to be a 2, 0, 3, 0, 4, 0, 5, 0, 6, 0. So for a 6, 0, my electron pair geometry is octahedral. What is my true molecular geometry? 5, 1. And a 5, 1 is a square pyramidal. Square pyramidal gives me an angle that's less than 90 degrees. throw some of these on the screen in a little bit here. Let's go to the next page. We got SO2. So if we combine SO2, it would look something like this. My total valence electrons. Sulfur, how many? What group is sulfur in? What group is sulfur in? All right, 16. So we've got 6 oxygen. We've got how many? What group is oxygen in? 16. So we can do 18 valence electrons. First thing is, we just got to connect these, right? Now, what do we got to do? We've got to add 6 around my oxygens, right? Complete the octets. So if I do that, oxygens are happy. Sulfur is not. But I've got how many electrons so far? I've got 16 out of my 18, correct? So on my next step, I got to do this first. So I did step 4. We place lone pairs around the central atom. If there are more electrons left, place as lone pairs. We got it. We have 2 electrons left, right? So we got to put them on there. Sulfur is a little bit more happy, but not quite happy. So I got to go on. So I just did step 5. If there are more electrons left, place them as lone pairs. I did that. Step 6, if the central atom has an incomplete octet, use the electrons from the surrounding atoms to make double or triple bonds. Okay. Now the question is, which drop in 2 electrons? Which oxygen do I take them from? That's the question. Well, first of all, let's take it from, let's just drop these 2 in. So I drop them in here. That. Okay. Sulfur's happy, yes? Right? Sulfur happy. Everybody's happy. Except for the rest of us. Here's the problem. There's a problem here. We know that if you have CH3CH3, if you have a single bond versus a double bond versus a triple bond, the bond length of the triple is shorter than the double, and the double is shorter than the single for the length between these bonds. Let me say that again. Or this is the greatest bond distance. I don't quite have the scale on here. This is a shorter bond distance, but this is the shortest distance between the bonds, triple bond. Now, however, we know for sure that the bond length, so if we drew this out, another way to draw it like this. Put a single dash there, double dash there with a pair of electrons. You might see it like that too. The problem is this. The way we drew this out, we would predict that this bond length between this oxygen and this sulfur would be shorter than this bond length. The problem is it's not. This has been verified that the bond lengths are exactly the same. So that brings us to this concept of resonance. So for resonance, you would maybe agree that if we dropped in this double bond here and took this double bond back out, then we have a double bond here and a single bond here, correct? Without going into a big explanation, if this thing can flip back and forth really fast, see a difference. So that's actually what happens. We know the bond length is exactly the same. What explains that is resonance. And now to draw a resonance structure, we put double arrows like this. So we need double arrows. And now we just flip it back the other way. So this time we're going to make, I got to put sulfur in the middle. I'm going to make my double bonds here. I'm going to make my single bond here. Again, for resonance structures, if you can imagine this can flip back and forth really fast, you will not see any net effect. The bond lengths then are exactly the same. So this gives us one resonance structure. Yes, a multiple bond for sure, but this gives us both possibilities. It just shows us both possibilities, right? It gives us both possibilities. So there's not going to be resonance structure 2. How many bonding domains do I have? Oops, I'm sorry. Hey, somebody should have threw my pen or threw a pen. I'm still missing that pair of electrons right there, right? Let me zoom back in. I didn't put those up there. Now it matches. Okay. How many bonding domains do I have? You got a double and a single. How many bonding domains? 2. How many non-bonding domains? On that pair of electrons, right? 2, 1. What is my hybridization for a 2, 1? What is my hybridization for a 2, 1? SP2, right? I'm just following my blue sheet, the 2, 1. What is my electron pair geometry? How many possible bonds would I have? 1, 1, 1, right? That's going to be 3 if there was a bond for this pair. So you consider that a 3, 0. And my electron pair geometry then is a trigonoplanar. My molecular geometry is a 2-1. 1 is going to get me bent at 118 degrees. All right, NO3 minus. And we got a negative charge on that, right? NO3 minus. My total valence electrons, how many for nitrogen? How many for oxygen? Nitrogen's in group 15, so we've got 5. Oxygen's in group 6. This negative charge, we got to add 1. (24 valence electrons. Let's put nitrogen in the middle. What's my next step? Make oxygen happy, correct? My next step is to make my oxygens happy on the outside. Breaks on now. How many electrons do I have so far? 4. Yep. Right. How many am I allowed? 24. Not happy. Nitrogen. What do we got to do? Slap a double bond in there, correct? How many double bond choices do I have? I got 3 choices, right? I've got 3 ways to do a double bond here. This is going to be then multiple bonds with 2 resonance structures. Because the bond angles here will be exactly the same as well. So let me go up here. First of all, let's do we'll put our resonance structure right here first of all. So I'm going to just drop it in. It doesn't matter where you put the first one. We'll do it on the right side. By the way, there will be a bracket with a negative sign on all of these, but it's going to make a mess, so I'm not going to do it. Oops. I better finish off. Right? Looking good there. Here's my first one. Okay. Now I'm going to draw this one up here. My next one, I'm going to turn around. I'm going to make this a single. Let's put my double down here. There's 3 choices, right? So now on my next one, put my single here. Double down here. Put my single over here. Last one right here. I got to put my double bond on my left, right? That's where I haven't done it yet. So I'm going to have nitrogen. Go this way as well. If this can flip back and forth, there's all my possibilities, right? In my double bonds in all three possibilities, right? So those are my three resonance structures, three possibilities. We do that because we know the bond angles are exactly the same. How many bonding domains do I have? 3, 0, right? It's a 3, 0. 1, 2, 3 bonding domains, 0 non-bonding domains. For 3, 0, my hybridization is Sp2. My electron pair geometry is 3, 0, right? And my molecular geometry is a 3, 0. So I'm going to put them together. 3, 0, 3, 0 gets me trigonoplanar and trigonoplanar gives me an angle of 120 degrees on that. Okay. We're going to talk about, because we need to do this before that, whether or not the molecule has a dipole, whether there's a bond dipole, a molecular dipole, and that gives us to this concept of polar versus not polar. And to really do this correct, we are going to add polar, non-polar to the right side of our blue sheet like this as we go down. So polar or non-polar is our question that we have to explain right now. Okay. With that, I think I'm going to try to do all of that, what I have on the screen here. So I'm going to stop this share and I am going to get off there, but that messes up my share, doesn't it? Share screen. Sharing the screen. Okay. Now, atoms have different electronegativities. What are electronegativities? It's the pull for these shared electrons in the middle. When I'm looking at this right here, if I turn this electric field on, right now, atom B's electronegativity is higher than A. We know that whoever has the highest electronegativity pulls the shared electrons towards itself. Here, B would get the negative charge assigned to it. A would get the positive charge. This could be sodium chloride. When we have sodium chloride, this would be Na, this would be Cl, +1 here, -1 here. When you see this bond dipole, that's just pointing where these shared electrons are going. So if I rotate this, obviously, if this is the most electronegative and the negative region it's going to be attracted to this positive plate. If the electronegativities are exactly the same, there's no attraction. If we look at real molecules, if we have HF, which is more electronegative, hydrogen or fluorine? Fluorine for sure, without a doubt. So if I click on this, my arrow tells me that. Fluorine for sure is negative. This is hydrogen +1, fluoride -1. If we look at that, here's all this negative charge. For sure is polar. When I click on this arrow, if this shows up, the molecule is polar. And it should be. Those electrons are not shared equally. Fluorine picks them up. Fluorine gets assigned the negative charge. However, if there's an opportunity to cancel them out by one pulling to the right and one pulling to the left, the net effect is it would cancel out. We can get a non-polar molecule. Or if we just have this situation, this is N2. That's non-polar. That is a triple bond in there. They're shared equally. Same way with oxygen gas. It's a double bond. Let's go to carbon dioxide. Look at this. Is there a bond dipole? Yeah. Oxygen is more electronegative. But look at oxygen's pulling to the right. This is a linear molecule, correct? This oxygen's pulling to the right. This oxygen's pulling to the left. What's the net effect? Non-polar. When I click on the yellow here, there is no true molecular dipole. Is there bond dipoles? Sure. What is a bond dipole? It's the pull for shared electrons. But this cancels out, right? In fact, we can put the electronegativities up here. Oxygen's 3.5, carbon's 2.5. So this is a non-polar molecule. If I go to water, this thing is polar for sure. Look at all this negative here. Is there bond dipoles? Yes. Which ones win in the tug of war for these shared electrons in the bond? Oxygen. Oxygen's pulling this hydrogen's electron away from it towards itself and pulling this one. You get all this negative charge up here. This has two non-bonding domains, correct? This thing is really, really polar. All right, let's move our way down. Here is BF3. This is an exception to the octet rule. What do I mean by an exception to the octet rule? Boron is a central atom that only has 6 electrons. That's it. Boron's happy with 6, not 8. This is a 120-degree angle that cancels out. It's 120 degrees. Fluorine is pulling here at 120. So the net effect is this cancels out. So when I click on this, nothing shows up. This is non-polar, BF3. So let's summarize. How do you end up with a non-polar molecule? Well, you need equal angles to make it cancel out, correct? And the terminal outside atoms have to have the same pull, which means they have to be the same. If I change a fluorine out for one other atom, it should not cancel. It will not cancel. Let me say that again. To have a non-polar molecule, they cancel out. How do they cancel out? Equal angles and equal atoms on the outside. So BF3, non-polar. Here's CH4. I'm going to click this, non-polar. Everything cancels out. That was this one, right? Everything cancels out. This is non-polar. Are there bond dipoles? Absolutely. EF4 would do the same thing. It's going to cancel out. This right here now is going to be polar. Why is it polar? because I don't have 4 atoms that match on the outside, right? So when I click on this, or I do have it clicked on, right here is my arrow. Remember, the outside terminal atom should be the same. Now, let's go to molecular shapes here. I'm going to click on my electron pair geometry down here. First of all, my electron pair geometry for this is a 4-0. This could have 4 bonds on it, correct? 1 bond here, 1 bond here. It has 1 bond here and 1 bond here. My electron pair geometry down here is 4-0, which is a tetrahedral. What is my true bond geometry? 2-2, right? 2 bonding domains, 2 non-bonding domains. This is bent. I go to the next one, CO2. We did this. Notice my electron pair geometry is a 2-0, and it is my molecular geometry is a 2-0, linear. We did SO2. This shows it a little bit different, but SO2, what is my electron pair geometry or my electron geometry? 3-0, trigonal planar. What is my true geometry? My molecular geometry is a 2-1, which is bent. Here is XEF2. Check this out. What is my electron pair geometry? 5-0, correct? I could have 5 possible bonds on this. If I have a 5-0, it's a trigonal bipyramidal. It makes 2 pyramids, right? If I cut out the bottom, it's doing a pyramid this way. And if I look at the bottom, it's doing a pyramid this way. Trigonal in the middle, 3 in the middle, pyramid going up, pyramid going down. What is the molecular geometry? 2-3, right? 2 bonding domains, 3 non-bonding domains. What does that give you? Linear. Question. Is this polar or non-polar? Can everything here cancel out? It does. Because if this is a fluorine pulling up, fluorines winning the tug of war. This is a fluorine pulling up, this is a fluorine pulling down. That would cancel, correct? And look at my non-bonded pairs in the middle. How many degrees apart are these in the middle? Those are 120s, correct? So 120 here along my x-axis, if you can visualize it, I'm going to rotate it. 120 along my x-axis is going to cancel out. We did this. This is NH3. This is a 4-1 for a molecular geometry, or excuse me, 4-1 for an electron geometry, tetrahedral, 3-1 for a true geometry, right? And if I go down, this one we did. This is a BR F5. We did this. Is this going to be polar or non-polar? Polar for sure. That can't cancel out. Just looking at it, you can see it can't cancel out. But if I go down to this, SF6, polar or non-polar? Can everything cancel? Everything can cancel, right? If I rotate this slowly, if you're looking at the middle of this, along an x-axis rotating, that's 90 degrees apart, right? In fact, everything's 90. So if you say this pulls up, this pulls down, but this would all cancel out. This would be non-polar. How about this one? This is a 5-0. Does everything cancel on this? Now, the last one, I had 90s in the middle, right? Everything in the middle like this was 90s. But if I go to this one, everything in the middle is, let me rotate it correctly here. Oh, let me get this like this. There. Everything in the middle is what? 120s. So my middle 120s are going to cancel out. My up versus down is going to cancel out. This would be nonpolar. You look at the pole on this, this would cancel out. Nonpolar. XEF4, polar and nonpolar. How many degrees apart are these non-bonded pairs as I rotate this? Now maybe you see it better. These are going to cancel out 180 degrees apart, correct? Those would cancel. What's my bond angle in the middle? 90. Everything cancels out on that. That would end up being nonpolar. We will fill that out on the right side of our blue sheet. I want you to get started on the quiz. On the take-home quiz, you can get started on that. You can now start cranking in some OWL and skipping around an OWL. I feel good that if you have one-day lab, you're going to have a grasp on it. Again, look at the lab ahead of time. It is an absolute beast. And on this quiz, try 1 through 17 on this quiz. 1 through 17. I'm not going to switch cameras for that. 1 through 17 on the quiz. Poke around at that. Poke around at the lab.